This week we have one familiar face and one new face to the temporal graph reading group, which will present the TGM temporal graph modeling. So I think everyone who's been to the temporal graph reading group before kind of know who Andy is, but I'll give Jacob an introduction as well. Jacob Chmura is studying Master of Computer Science at Mila under the supervision of Professor Nicolas Leroux and Professor, I'm going to butcher that name, Reinhard Rebani. He spent the last 4 years working as a machine learning engineer in deep reinforcement learning at RBC, where he led research, architecture, and development of an end-to-end smart order routing system. Before that, he developed a patented multitask reinforcement learning framework for personalized trading that enables few-shot adaptation to client trading preferences. His long-term goal is to build embodied decision-making agents that emulate human-level generality inspired by the recent advances of foundation models. He's also fascinated by the intersection of machine learning and computer systems and building ML software that scales. Cool. Take it away.
Okay, great. Thanks for the introduction, Victor. And I will leave you guys to let more people in. We got a lot of bots as well for the note taking. But yeah, thanks for coming to the talk, everyone. I'm very excited to talk about TGM here today with Jacob, who is also the co-lead author and core contributor on the library. So so I want to talk about TGM, which is modular and efficient ML on temporal graphs. So if you don't know, TGM is a new ML library for temporal graph. And this is also will enable you to do much easier temporal graph learning. It already supports a large number of models, and I will give you more details over the talk. And you can already start playing with it. We are in the beta form now on our GitHub, and you can also do a pip install to just play with it on your end as well. With that being said, I will start by talking about the TGM team. So thanks to everyone who contributed to the TGM work. So Jacob and me are the lead authors, and then also Bao and Ali helped with a lot, and then Farma, Yuri, Michael, Guillaume, Matthias, and Rehane all give feedback and supervision on the project. Um, and for the talk today, I will break it down into three parts. So I will cover the first two parts, which is the background and motivation for TGM. So how we get to this point, why we want to make a new ML library, right? And then I will, for the last part on how to get started and how to use TGM, I will leave it to Jacob to give you more details. So first of all, a mandatory slide on temporal graph learning. So we know that we have a lot of data in the world, and we have billions of users and messages and information that are changing every day, right? So basically, we want to learn over these information. And in the field of temporal graph learning over the past years, and for attendees of this reading group, we see a lot of improvements on different aspects, exploring different research directions on temporal graph. And to power everything that we do in temporal graph learning, we need to have a solid library and software tool, similar to how static graph have geometric, and DGL. So we want to have a tool that works for temporal graph as well. And just to give more on the background side, I think many of the audience might be quite familiar with this already. But I will talk about the two representations, which also both are supported in TGM. And I will get into how it's supported in a bit as well. So we'll first talk about continuous time dynamic graphs. So in continuous time dynamic graphs, here we consider the dynamic graph or temporal graph as a stream of edges. So you have your source destination and your timestamp. This represents a chronological order of sequence of events. And also, very importantly here, which is often not explored, right? So in the TGB work, we also mostly focus on just sequence of link interactions. But in the real world, we also have node events or node interactions. So so the link events are basically you have, the standard graph edges, source destination, and timestamp. And for node events, you also have a node and the timestamp, which is changing, as well as an associated feature on this, right? Uh, so to support both the node and link events, it's actually a non-trivial thing to do, and most of the existing library cannot do that. So in TGM, we're actually the first library to support dynamic node features or node events natively in the library. And for continuous time dynamic graphs, because of the streaming nature of it, it is very useful for online or streaming setting, or even just a very fine-grained setting, like you have interactions that are second-wise and so on. Uh, and and there are many methods developed for continuous time models. These are more referred to as event-based models. And then we have discrete time dynamic graphs. So discrete time dynamic graphs are more similar to your static graph setup, where you have a sequence of graph snapshots. Here, the sequence is very important because the sequence order of the sequence tells you the chronological order of events and how the graph structure changes, right? And then each of the graph snapshots then have a set of nodes and edges. Uh, be aware that this set of node and edges might repeat. So you might have the same set of node across time. They might not. They could change over time, right? So these are generally two different views of temporal graph. And the discrete time dynamic graph is more referred to as snapshot-based models. And people in DTDG literature more explore it as data sets where you have fixed time intervals where the data arrives. So then you kind of group them into the snapshot and you process them in the sequential fashion, right? But one motivation for the library and why I started to work with the TGM team from 1 year ago or even more is that a lot of the temporal graph models are very disjoint, right? So looking at the literature, so this is the survey from 2023. So we see that the temporal GNNs are breaking down into snapshot-based, which is the DTDG ones, and event-based, which is the continuous time ones, right? And and when you are doing research in the space, you are very aware that continuous time models almost always just compare with continuous time models. Discrete time models almost always just compare with discrete time models, and there's very little cross comparison across the two categories. And that's one of the motivation for a new library is that we want the library to support both type of models. And as we'll see later on, they are really not that different. They are just different ways of looking at your data, different ways of processing your data, and many of the architecture, like recurrent units, like the GNN parts, are shared across both type of families. And I hope going forward with TGM, we can design models uh, that can work across both settings or take inspirations from both settings to kind of be most efficient and also can have the best performance. Okay, so uh, here's another motivation. So we know that many of the research is accelerated by good software, right? So in deep learning, it really the big boom come from when I started, it was in 2018 and 17, it was more TensorFlow, and then we have PyTorch, which make life easier to code up many of the layers. And then in earlier, you have Caffeine, right? And then for graph learning, we have geometric, we have DGL, which is very widely used in the community, right? And for temporal graph learning, there are many different libraries, but I think we still are looking for one that is very good for research, that is well designed and efficient, and we can really adapt it and grow it over time, similar to geometric, where it adds more functionality, support for heterogeneous graph, and more, such that it makes it can accelerate the research and have a standardized system of workflows and module layers and so on, right? here I will do a very quick overview over temporal graph learning libraries and kind of how we get to this point in 2025, right? So in the very beginning, not the beginning of time, but early on in temporal graph learning research, so we have two big libraries, right? So we have PyTorch geometric temporal. So PyTorch geometric temporal focus on more spatial temporal graph task, and also it focus on DTDGs, right? The snapshot-based models. It supports a wide variety of models. Um, and some of them you can find like very good implementations there, right? But they do not support continuous time models, which then become much more prevalent later on. And then we have PyG, PyG extension to temporal graph, right? So PyG has extensions to various different types of graphs, and one of them was temporal graph. And there's the temporal data structure, which if you work with TGP, you will be quite familiar with it. That's the data structure that kind of gives you, the chronological edge list and so on. But in PyG, it mostly work with continuous time models. It supports a few models like TGN and I think also Graph Mixer. But there's a limitation in terms of model variety, though the PyG implementation of neighbor sampling and so on are very efficient, as you can expect from PyG. And then in 2022, there was the TGL library from Amazon. So there was a bit of interest in scaling temporal graph models into billion scale. So this is one of the first work that I saw that work on very large scale temporal graphs. And in the paper, they show that you can scale TGN to billion size graph. However, there are some caveats where, as you may know in the field, many of the evaluation is very link prediction dominated. So most papers only evaluate on link prediction. And also, um, the evaluation for link prediction is also not very good because you are doing a kind of binary classification on, the true link and a random negative, right? So there are some limitations on that. But regardless, in that case, it's one of the first most scalable library in TGL. And then we have distributed TGL, which is a very interesting paper, but I won't go into too much detail. The idea is that it does a very smart way of supporting distributed GPU. So you can put your temporal graph batches across multiple GPUs in a smart way, such that you can use the scaling of GPUs and going beyond a single GPU, which is most temporal graph models does. But this is also more specific to specific architectures like TGN. And then we have DigiLib, which many of you are quite familiar with in your research. So DigiLib was coming out around the same time as TGB, and it focused on continuous time models. Um, and and the DigiLib code, despite supporting many different models and widely used, are not very modular, right? So you have a lot of hard-coded if-else statements on, okay, you are this model, go do that, and so on and so forth. So it's not very modular and it's also a bit slow when you run it for experiment. And then in 2024, we have TG Lite, which is a new library that focuses on a lot of optimization. So getting rid of redundant operations, right? Improving over the workflow. And they really specialize and make it much faster to run for specific models like TGN and so on. And it's very scalable as well. Um, and okay, going through that history, there's a few questions, right? So first of all, if you look at it, we only have libraries that work for either continuous time or discrete time. So not a single library that can do both. So if you are a new researcher or if you want to deploy your model for a new data set, which type of family of models should I use, right? Which library should I pick, right? Because the ones that support the most recent models might not be the most efficient one and so on and so forth. So there's a lot of friction there. The second question is, can we have, as I mentioned, a model or a ML library that support all the temporal graph models, right? Or make it very easy to support. So that's kind of one of the vision for TGM as well, because by unifying both category of models, we want to support all possible temporal graph models, um, and make it very easy for community to contribute to TGM to add new models, um, like we see in PyG, right? And then lastly, we want the library to be research oriented. So you have a lot of flexibility in things you want to do. So you want to have your own specific neighbor sampler. You want to add specific features and idea. Um, yeah, and so on. So we have a question from the audience. I will quickly take. So how does the continuous and discrete time models different? That's a very good question. I can give you a very short answer right now, but for more details, I suggest you can go through. So I have some lecture notes on my website, which go through more on the details on the model. But essentially, the continuous time models, they work with fixed size batches, as in each batch is like a fixed number of edges. Because in the continuous time case, you cannot form graph snapshots very easily because you have a continuous interval. So the models then just say, I'm gonna not do anything until I accumulate a fixed number of edges. And then I design models to work in this fashion to always process this fixed batch size um, of edges, and then they will do some temporal sampling and recurrent model and so on. So the snapshot-based models are more different in the sense that um, you would use a standard GNN, and then you would have some way to evolve your GNN embedding over time. So the GNN are working on sequence of graph snapshots. So each of the snapshot is simply a standard graph you can feed into a GNN, right? So then the question is more about how do you evolve your graph embedding over time? Yeah, so hope that give you a quick answer on the breakdown on those. Okay, so now I'll get into yeah, so we kind of talk about that a little bit already. So why do we want a new library for temporal graph, right? So we see that we want software acceleration on the research, right? And we want to solve the fragmented ecosystem in temporal graph learning. So we want to standardize the workflow pipeline. And also this will help with like evaluation and model reproducibility and how you can how when a new model is presented, instead of just its own GitHub or its own separate way of implementing, neighbor sampling and so on, if it have a centralized library, then it's much easier for you to bring this model and test it in many different cases, right? And then also current libraries are too specialized or not efficient. So they are either too focused on specific type of models like TGN and so on, or they are not very efficient like DigiLib, which is relatively slow when you uh, run for more robust evaluation, right? And also the current ecosystem lacks many of the tools and features that we see from more mainstream ML domains, right? So like a continuous support on the library, right? So a library being continuously supported and adding new features to evolve, right? And like having issues on GitHub and different versions and yeah, and releases and unit tests and so on. So these are kind of the main motivations. So now I will talk about TGM. Um, how are we doing on time? I just want to make sure we have time to get to Jacob. How much time do we have?
We have 40 minutes left.
40 minutes left. Okay, good. So I think should be fine. Uh, okay, so basically to put it on a timeline, here I will talk about TGM. So here's a few quick breakdown about many of the things that are new to TGM. So first of all, the TGM is the first library to support continuous and discrete time models. As I mentioned, TGM support dynamic node events. So for the first time, you can actually have a native way um, to add in changing node features, which is not possible, for example, with PyG, right? And then you have the support for link, node, and graph level tasks. So if you go on the TGM GitHub, you will see example folder have link, node, and graph tasks, and you can see how the library can run various models on these tasks. Um, One key thing that we support in TGM is time granularity, which I will go into more details. So TGM then support time granularity on your data as well as time granularity conversions. And then we have event and time-based data iteration, which goes to how we support continuous time and discrete time models. And then um, a very important feature of TGM are hooks as data transformations. So basically, the concept of hook is that you take a batch of data. So imagine you have your graphs snapshot, and then you apply transformations on the snapshot. So you can add new attributes. You can compute some statistic on the snapshot. You can sample neighbors. You can do various things, and these data transformation then allows you to basically have a standardized batch object. It's very similar to what PyG does, right? And then from this batch, you can then feed it to your model. So then the model can get the required neighbors or information that it needs to process the data. And here's some quick comparison. So basically, uh, so many of the previous libraries are missing many of the features that I was talking about, and I think just to show on the TGM side, we have profiling, we have unit test, and we have integration test, and so on. Um, so so we built it to be a more software library. So I treat it more as kind of like a software project than a research project, though it has quite a bit of research component as well. And these are the core features, as I mentioned, and I will go through them like one by one. Um, so 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 the first one is that in TGM, everything is represented. So this is the raw storage of TGM. So we store temporal graphs, not specifying them as continuous time or discrete time. Actually, in the storage level, you don't care about that. What you care is what is your input data. So input data is simply edge events and node events. So as I mentioned, edge events are basically the link information. So each link has some timestamp associated with it. And then node events uh, are node features that happens in a specific point in time. So it's node feature with a timestamp, right? And in TGM storage, we store them um, both by sorting them with time. So when you are iterating through data in TGM, you are going to get both link and node events, like edge and node events. Um, and the static node features also exist. So I don't show in the visualization here, but similar to static graph, you also have node features that do not change over time. So these are separately modeled as static node features. Uh, and uh, and you can view the temporal graph as the dgraph class in TGM. And then we have different neural network layers. So this is just the models that we already support, like TGN, TGAT, TGCN, GCLSTM, TPNet, and IGFormer. So you can check them out on the repo, and we have examples for all of them on how to use them. Um, and I want to talk about the time support in TGM. So in TGM, it's built in the sense that temporality support or timestamps are one of the most important component. And in fact, timestamps are required as input. So all the information you have in a temporal graph, you must have timestamps. So this allows us to chronologically sort them and then support different time operations. So you can use time to do data organization, as I mentioned. So sorting the edges and events, and the storage will then store the events in a chronological order. And then we have data conversion. So here, your input data have a native time granularity of a data set. So for example, let's think about the UCI data set. So in the UCI data set, it's a social network, and many of the timestamps are continuous. So in the sense that the raw timestamps of edge events are, Unix time or something like that. So that's what we call a native time granularity. So when you are loading the data set, you will specify the native time granularity of the data set. Okay. And then once you load this data set, you also have the option to discretize it. So maybe you want to say that my data is second-wise, but I want to have daily snapshots, or I want to have timestamps um, that are based on which day it is. So then you can discretize your second-wise timestamp by remapping them um, into daily timestamps. And then we have the last point, which is time as data iteration. So when you are iterating over this UCI example, so you have second-wise timestamps. Now you're iterating it, right? Um, you can iterate in two ways. So one way is kind of continuous time where you have 200 edges at one batch, and then so on and so forth. You could also iterate by time. So when you iterate by time, TGM is going to say, I'm going to group all the edges in a given time granularity, let's say daily. So for a given day, I'm going to look at their second-wise timestamp or Unix timestamp and check for all the edges in that day, and then give you the entire um, batch of edges for that day. So that's iteration by time. One quick note, there's a specific time granularity, which is called ordered. So ordered time granularity means that there is no real world timestamp. So you don't know the time granularity of the data set, which could happen for example, for privacy reasons. So you only know that, okay, my data set is ordered in this way. So the edges have this ordering, but I don't know what is the meaning of my timestamp. Is it second or hour or daily? I don't know. So in that sense, you can still work, but for the order time granularity, you cannot do conversion because you don't know the actual real world meaning of the time. Okay, so that's just one quick note on that. And here is one example of doing the discretization that I mentioned before, right? So here is the same set of data stream. So so on the top, this is like the continuous time stream, like more like a stream of the raw timestamps, right? So you can see that for the same data set stream, you can iterate by events. When you set batch size of 3, it means that I'm always going to give you a batch of 3 edges. And you see that the effect of this is that actually none of the batch covers the same span of time, right? But you guarantee you're going to have 3 edges in a batch. The second way to iterate is iterate by time. So when you iterate by time, you would group all the edges in a fixed duration. So here you see that the duration is the same, but the amount of edges in each duration might be quite different. And then you can perform a discretization. So discretization is different by iterate by time because iterate by time do not change the timestamps or the data itself. But discretization will change your data by removing redundant edges. So if you look at the first bracket here, you have this orange to blue and green to blue, and they are discretized into just orange to blue and green to blue. So just 2 edges. So you actually remove redundant edges in the discretization case. So we support all of these APIs, and you can play with it. Okay, there's a question on why so much stress on the edges. Is it something specific to the field? Well, edges are one of the most basic concepts in graph learning. So this also the most, well, it's the finest grain data unit that you have, right? So when you want to iterate, the smallest you can iterate is by 1 edge at a time. So that's why, and then the grouping of edges then become different ways of looking at the data. So that's essentially what it is. Okay, so um, yes, so grouping by node, yes, so that's also because the edges have timestamps. So that's why you group by edges. You can also group by node, but that will be more like neighbor sampling. So it's kind of orthogonal to this because node inherently do not have timestamps. Nodes are defined by their interactions, which are edges, which have timestamps. Okay, uh, going forward, so this is what we see. So now by this formulation, iterating by time, then allow us to run discrete time models which process snapshots, right? Because you have graph snapshots defined over each of the time interval. And then we have iterate by events, which then allow us to model continuous time models, to run continuous time models. So in this way, TGM can support both type of models. Yeah. And then just as a tip, when you iterate by time, you can also specify different time granularity. So you can say hour, daily, depending on what you want to do. Yeah. Okay. One last aspect I want to emphasize on TGM is the hooks aspect. So hook is a new concept that we introduced in TGM. Um, and and here's how hooks work. So so hooks are inserted into the workflow in the following picture, as you see here. So you start from your temporal graph, which you view over the storage. Um, and then the storage is feed into the data loader. The data loader then process you one batch at a time, as I discussed. And then on the batch, you then perform hooks to add attributes to your graph or add transformations to your graph, right? And then these hooks then can give you neighbors, can give you negative samples and so on. And then this unified batch notion are then used to feed into the TGL models. So here's two example. So we have the TGAT link prediction. So to run TGAT, you need the layer itself, but you also need two ingredients for link prediction. One is the neighbor sampling, which the TGAT layer requires. So this samples temporal neighbors. And then one is the negative edges. So this is what you use for training and evaluation. So you need to have negative edges, which are edges that don't exist, uh, to compare with the true edges that exist in the graph. So the hooks, the negative edge sampler hook will produce the negative edges in batch.negative. And then the recency neighbor sampling hook will produce the neighbors, which are batch.neighbors. And then with those, then you can run TGAT layer. And you can see the detailed example in the script here. And then the second thing is density of states. So this is one example of a data analytics. So here we want to show that with the same hook transformation, you can actually do data analytics on temporal graph as well. So again, you take your batch, which is a graph snapshot or some definition of the batch that you iterate over. You can then look at the edges in the batch and then form your Laplacian matrix. And then once you look at the Laplacian matrix, you can then compute some statistic, which in this case is density of states estimation from my prior work, just as an example, right? And then you can have this over multiple batches to look at how this graph property changes over time. So the example is available here. Um, and and for the last part, and then I will hand over to Jacob, is the system design for TGM. So this gives you a high-level overview of how the different components in TGM work together. So we start with the data layer. So in data layer of TGM, um, you start by doing I/O. So you would load from some data sets. So we natively support TGB data sets. And then you can do CSV or pandas. And then in the future, we also plan to have more I/O adapters, so you can load more existing data set very easily. And then we do pre-processing, which includes splitting the data into training validation test as standard. and then you can do discretization there as well. So you can remap and change the granularity. And then this raw data is stored in the COO format and chronologically sorted. Um, and then this storage is then sliced to form a graph view. So graph view is the dgraph object, is uh, the main object that you work with in TGM. So there basically it provides a view of the graph. So it's saying that you have a starting time and an end time, and this is the amount of data that I have the view over. So kind of like how you would slice a tensor. One thing I want to point out here is that the TGM is designed in a way that it's backend agnostic, which means that so even though currently we have a single backend, we can support different backends such that you can have better complexity on some of the operations that you do. So, for example, some better sampling on the nodes or some better sampling for a specific operation that you want to do. So, so it is possible to change the backend for TGM to achieve that. And the second part is the execution layer. So the execution layer first start by defining the hooks. So basically, you can register your hooks manually, or you can use existing recipes, which is just a predefined list of hooks. And then the hooks are managed by the hook manager, which checks, can I do these data transformations in sequence and if they are valid or not? And then the hook manager is running on the data loader and then process each of the batch, right? So the hook manager manages the hook dependency and ensures that the transformations are possible. So for example, if your neighbor sampler requires negative um, samples, they must already be produced by negative sampling hook. So there's a sequential fashion of the data transformation to ensure that that is valid. And then lastly, um, we get to the machine learning part. So once the transformations are done, it produces batches which are put into the GPU, right? And then the batches are feed into models. So the models takes a TGM DG batch object. The DG batch object are then used for your forward pass, as you are familiar with. And then it produces model outputs in terms of link, node, and graph task. And then you can do different evaluation and so on. And in the future, you can also support more types of tasks and evaluation and so on, and more layers as well. Um, yeah, so I see there were some questions. Um, Okay. One question from Hussein. So what about features when performing discretization? That is a very good question. So, this is an optional argument you can work with. Currently, we support that when you are removing redundant edges, you keep the first edge as reference point, so you kind of get rid of the other ones. But of course, you could do a sum, you could do a max, you could do whatever set operation you want to do on redundant edges when you are discretizing. So this could become an optional argument. So that would be a small change in the code as well. Um, so basically, the TLDR is that you can specify your custom way of doing that, the custom way of handling the features when you do discretization. Um, is there an easy way of converting a PyG or Network X object already into TGM? Um, so That's a very good question. So basically, you can use all of your PyG layers. So PyG is essentially, so PyG data loading is essentially like edge index and features on the batch. So very similar to the TGM batch. So you can actually use all of the PyG neural network layers because as long as the input works, right? Um, and in terms of converting PyG into TGM, so I don't think it really is useful if you want to feed a static graph, which most PyG graphs are static graphs, so they don't have a time component. So if they don't, yeah, so if they don't have a time component, it doesn't really help you when you feed it into TGM um, so because TGM have a emphasis on the time granularity and the time operations. But if you have a sequence of edge index, right, from PyG, um, you could just assign timestamp to them, and then you can feed them into TGM. Though we haven't written explicit support for PyG and Network X graph object into TGM, but this can potentially be added as I/O if that's helpful for some use cases that you have in mind. The transformations are available after batch. Is it possible to get statistic over the whole data, not only the batch level? Yes. So I didn't talk about it, but you can slice the D graph itself as well, and you can also get data from the D graph. So all the data is in the underlying storage. The data loading is just one way for you to iterate over the D graph. But you can also write your own custom query. So you can do dgraph.slice time, which then slices a chunk of data. So let's say a specific custom time range, and then you can look at the number of nodes, number of edges. So I will point you to the doc website to check out more on things you can get on the statistic there. But yeah, uh, you can definitely do that. How are static edges considered in TGM? Referring dynamic graphs with both dynamic and static edges. What do you mean by static edges? As in so you have some set of edges that just exist for all timestamps? I'm not sure I follow for that one. So maybe type more detail on the chat, and then I will get back to it. And for sake of time, I will quickly wrap up the experiment section, and then we can have more answers at the end as well. Yeah, so here's a quick numbers on the training time comparison. So this is just for testing efficiency. So very quickly, we see that TGM is about uh, 4 times faster than DigiLib, and sometimes like even more than that. Um, and TGM is very competitive with the very scalable and optimized TG Lite and TGL library, and we support many different models already. And here are some reasoning for why TGM is fast. So yeah, um, so we designed the library to be very efficient to use these software engineering aspects to ensure the efficiency. Um, I think I will get to this like kind of in the end because we don't have time to go into too much detail here. But essentially, we have very fast storage, and then we have efficient way of using the hooks to to um, to make the data loading and processing efficient. Um, and then we also do some optimization over the neural network workflow as well. Yeah. And here's one example of how we can use the time granularity. And this just shows that when you use different time granularity, even the GCN can get pretty strong performance in relation to the state-of-the-art models. So when you use the right time granularity, GCN on the Wikipedia data set can get to about 70%, and the best model, state-of-the-art model, is about 82%. So this just shows you how important to consider time granularity and the way that you are training the model and over different differences in time granularity. Okay, I will hand it to Jacob now. Sorry for the delay. Do you want to share your screen, Jacob?
Yep, perfect. So hopefully everyone's convinced now to start using TGM. So you want to learn how to get started. So we have just a couple of slides here to help you figure out how to orient yourself. So first of all, when it comes to installation, we basically have two options. You can use the latest release from PyPy by installing TGM lib. And alternatively, you can get the most up-to-date features and bug fixes by directly installing from our GitHub. Up until now, there was quite a bit of changes going on as we were developing early on. Now that we're relatively stable, we plan to increase the frequency at which we do releases, especially as community involvement continues to go up. So you can expect the updates to become more frequent. Once you've set yourself up with TGM, you should kind of just always have like a tab open with the documentation. We spent a good amount of time trying to make it really easy to navigate. So we have a full API reference, details about some of the design decisions we've made and the architecture, and also put together some tutorials going into some of the more complicated aspects, such as graph construction, managing of time, and the notion of hooks. So probably with this presentation, you have a very high level and vague understanding of what we're trying to do. But these tutorials walk you through everything end to end. So I encourage everyone to check them out. Also, I think Andy mentioned we have quite a few examples that can serve as a starting point for your projects. We have usage of TGM from an analytics perspective, as well as graph prediction, link, and node prediction. And these are standalone Python scripts, so very easy to copy and paste, very lightweight, and they're also integrated with logging and profiling out of the box in case that's something that you're concerned about. Quickly now going through the tentative roadmap of what's coming in the pipeline. In the short term, we're looking to add support for heterogeneous graphs, which is something that a lot of researchers are interested in. So this is our short-term goal, as well as expanding some of the analytics. So if you guys are familiar with Andy's other work, TGX, a lot of that can, sorry, a lot of those statistics can be ported over into our infrastructure. And now you basically have this single spot where you can come to for both analytics and machine learning, and make it much easier for you to understand the relationships between graph properties and model performance. Model expansion is kind of an ongoing thing. So we're continuously looking to add more models into the library, as well as inference optimization specifically for the TGB evaluation. And then slightly longer term, we're looking to scale to potentially industry scale graphs. So this will require things like offloading to disk, distributing the graph, potentially leveraging PyG 2.0 stuff. And just to be clear, what we have currently, everything we assume fits in memory, but this is more than sufficient for all of the data sets from TGB. So it's already more than enough to get started for research. And then, of course, this is all what we have planned, but the goal is to figure out what is actually most important to everyone here, to the community. So if you have a research project, if you have a feature that you think is missing, we're happy to prioritize it in order to drive the direction of TGM. And we also have detailed contribution guide if you want to actually help development of TGM, but also if you want to add your own models into the core library. So we're happy to walk you through that. We do have quite extensive test harness, so we will ask you to do things like write unit tests, but it's going to be in your best interest because once your model is added, it's going to be within our integration test pipeline. So not only will you have a better understanding of how your model performs under different workloads in terms of scale, you'll know where the bottlenecks are, and then you'll have some confidence that we will continue to maintain it and have an understanding that it's still correct. So we have a little bit of a demo, but we can also just pause here if anyone has any questions from what we've presented so far before we leave the slides and go into the demo. There's some questions in the chat, but I think Andy's answering them. Yep.
Yeah, I just wanted to say I think we're pretty much up to date with the questions, and then the final one.
Yeah, so just an answer to integration test pipeline. So basically what we have running periodically is all the models which are supported in the core library across various scale data sets. We'll just run a single epoch of training and we will ensure that the performance is roughly in line with what we expect. And this is periodically triggered when we make changes to some of the core library. And we also get out of it profiler results. So basically, you can be confident that if we change anything in the core library and it breaks something with your model, it will be caught early. And at the same time, if you make some change to your model and you want to quickly test it to see how did it change my performance, how did it change the efficiency, you can get those numbers very easily and just clearly see like an A/B. So it makes it much more convenient. Okay, so yeah, I'll switch to the demo. Let me see. Okay. Let me reconnect, sorry. Okay, so obviously we don't have time to go into too much detail. So what we've tried to do is give you a sample of different models with like sort of starting with the simplest to give you an understanding of the flavor of the code that you'd be writing and how TGM looks. And just to be clear, this is essentially just copy and pasted from our examples. So if you want to see the complete code, I encourage you to just go there. As I walk through, if there's any questions, just feel free to interrupt me and stop. So starting with edge bank, very simple baseline for link prediction. Here we have some parameters. So enable logging, a generic utility will give you some output from the entire TGM library. Setting the seed so we can run this. We'll be running on the wiki dataset. Okay, first step is going to be to load a graph dataset into TGM. So we basically have dedicated I/O from TGB, which makes it very easy for you to load a dataset by name and then use the native splits provided to you by TGB. So this basically gives you the raw data in terms of this DG data object, which is basically just a store of tensors. And once you have each of these data sets, the first step is to create the D graph, which is, as Andy said, sort of the central object. In this case, we're going to create it on CPU because EdgeBank is not really trainable. So we can just create these D graph objects here. And what this does under the hood is it creates the COO backend, the storage backend. But this is basically your starting point for all of your graphs. The logger gives us some high-level understanding of what is the time range for each of the splits, how many events, how many edge events, how many node events, and so on. So now we have our data. Now we're going to set up the hooks and the data loaders. As Andy briefly mentioned, basically the hook manager is the object that injects the dynamic behavior that you want into your data loader as you're iterating your data set. So what we're doing here is we need to add the TGB negatives during data iteration because this is ultimately how we're evaluating the model. So we create our hook manager with validation and test keys, and we register this negative edge sampler hook. It takes in the data set because these are sort of predefined negatives according to the TGB library. So basically for the validation key, we set up the validation negatives, and then for the test key, we set up the test negatives. And then this gets forwarded into the data loader. So what does the data loader take? It takes the graphs that we constructed, a batch size, and the hook manager. And now what this does under the hood is as you're iterating your data, you'll see that we basically materialize all the output of these hooks that you require. So at the point where you actually feed it into your model, you have all the tensor attributes that you require. And this is just showing that the data loader is using a batch size of 200 with a unit of R. R here is encoding the ordered granularity. So this is iteration by events. So we're basically giving the model 200 events at a time. Now we can initialize edgebank. So from tgm.nn, import the edgebank predictor. What edgebank does is, it essentially just remembers exactly the edges that it saw during training. So how do we give it the edges during training? So we do something called materialization. So materialization basically takes the view object, the D graph, and it actually creates a copy of all the tensors and materializes the specific subgraph that you need. One of the questions was about how do I get statistics or information on different components or different pieces of the graph. Under the hood, it's all about materializing specific subgraphs. So if you're using your data loader, that's essentially what it's doing under your hood, but you can also just materialize the entire graph. Of course, this will require extra memory. So typically you don't want to materialize the entire graph. But in this case, for instance, we need all of the edges from training to feed into the edgebank model. So we materialize the graph. We don't actually need the features in this case. We just need the edges themselves. And then the edgebank model takes the source, destination, and timestamps. So now the edgebank is basically filled with memory and it's ready for evaluation. Okay, we run evaluation. So this is what the evaluation will look like. Essentially what we do is we activate the hooks that we're interested in running. So if you remember, we registered a validation hook and the test hook. So in the case of validation, we're going to activate the negatives for validation and then call this eval function within the context. And you can see it basically runs the function and produces some MRR number. And the exact same process runs for test. In this case, we're activating the test hooks, which gives us the test negatives. So what happens? Well, basically, you can see here, as we're iterating our data loader, at this point, when you actually get the batch, you already have all the stuff you need. So if you were to add additional hooks, maybe you want some neighbor sampling, maybe you want some custom tensors for your own research, you can just create a hook and dynamically add this. And then as you iterate, this batch will have the attributes that you're interested in. In this case, the attributes are this negative batch list. And then this is kind of details around constructing the batch queries for MRR link prediction scoring. But the key takeaway here is the understanding that as you iterate your data, under the hood, the hooks will execute and give you the components that you're interested in. So in this case, we're essentially just asking the edgebank model to predict according to its memory. I'm also just showcasing here, we have some profilers like log latency. Again, it's another thing that runs under the hood, and it basically gives you some stuff like the execution time. We have other profilers as well for GPU and other stuff. I wanted to go through TGAT and some GPU stuff, but we're on the hour, so I think we can wrap it up here and see if there's any more questions.
Is there a link to this Google Colab? Is it in the documentation if people want to give it a spin themselves?
It's not directly, but I can copy the link right now and put it in the chat. And then also, again, this is kind of walking through the examples from the folder on the GitHub, so you can see the entire thing there. If you want to break it down like cell by cell, I can also just copy and paste this collab so you guys can check it out.
Yeah, we can link this to the README, I think, in the repo or something.
I think that would be nice for people watching the video later. But if it's the examples that are in the GitHub repo, then it's up to you guys how you do it. But
it's already in the GitHub repo. But yeah. Okay. Thanks for coming to the talk and all your questions. It's very good questions. We addressed some of it. If you have more questions, feel free to reach out. We are available on Slack, on TGL Slack, by email, GitHub. You can always raise issues. We welcome your implementations. So if you want to add something to TGM, you can check out the contribution guideline. It's quite exciting, and in the future we want to support more things such as heterogeneous graph support, knowledge graph support, um, and so on and so forth. So I think it's very extensible, and yeah, and thanks, Julia. If you want to work on the knowledge graph support, let us know. But yeah, so I think it's quite exciting, and honestly, in my experience, using TGM has really helped a lot with doing research. It's much faster and easier now. But that's just my personal bias. So thanks for coming to the talk, everyone. And yeah, have a great day.
Have a great day, everyone.
Thank
Bye.
you very much. Have a good day.